between these two. So the table here, it says keep the mass constant. Let's see. So we're going to change this to I don't know. We'll change this to a 2 kilogram mass, and we'll just use 2 kilograms for that. That's not what we want. All right. So 2 kilograms. String length. String length is 5 meters. That sounds reasonable. And then the bob height. I don't really know what that is. Do you know what that is?
The what length?
I'm just looking at this table down here. Bob height M.
Oh, meters. Let me check this real quick. Bob height. Okay. All right.
So I'm gonna just start this thing. Oh, it's moving really slow. Okay, we don't want slow motion. So you can see this thing moving back and forth, and the amplitude is 10. I don't know what 10 refers to, but the amplitude is 10. Okay. I don't know if you're seeing my screen. You see this thing kind of moving back and forth. So the amplitude is 10. The other quantities we need are the time. So I guess that's the oscillation period, 4.49 seconds.
Mm-hmm.
And then the max speed we calculate from this right here. Although I don't know where we get the angles from. This gives velocity. So you can actually see it's calculating that. Energy is calculated, kind of moving back and forth. Force is calculated as well. So what I am not seeing, and to help you, is are we just supposed to record? And we probably are. We're probably supposed to record the maximum speed. So if we go back to velocity, what's the biggest number that it gets to? It looks like 1.22, maybe. Yeah, oh, there, it's right there, 1.22. And then potential energy, we can switch to the energy diagram here. The total energy is always 1.49. So these two numbers add together to give you that 1.49. So that's, I don't know, is this a delta E? I don't really know.
Yeah, that is a delta E. For some reason, it's cut off.
Yeah, so if we like pause it right there, you could say 0.848, 0.646. Okay, I still don't know what this bob height is in meters. Don't know what that is.
I'm gonna ask a classmate about that because I have no idea.
I can look here and see if might be this number here in elongation.
Well, it is meters. That's what it says. Bob height.
So we can go with that one if you want. That will clear that up for us. Okay, so we continue.
Do we add mass like up to 3, 4, 5, 6, 7, or whatever?
It wants you. It says up here to keep this mass constant for all trials.
Oh.
So we're gonna do that for all of them.
So we're gonna be messing with the amplitude. Is that what it says?
It seems to say that only 6 different amplitudes and the corresponding times to pass through the lowest point of the swing. So if we change this amplitude now to, I don't know, 5. I guess I can't edit it. Reset. Okay. So that goes back to the beginning. The length. Did I change the length? I did. Okay. So we'll keep that 5. And then the rest of this we filled in. So The amplitude is now 5. Let me just read this one more time, make sure we're giving everything. Vertical distance the bob falls, that must be the bob height. Maximum speed, gravitational kinetic energy, okay, as it falls. All right. Okay, so let's start this again. So you can see the elongation is 0.436. That's less now, and that's because we changed the amplitude to 5. Now the time comes from where does, oh, there it is. It's
Oscillation
4.49.
period.
Yeah, it seems it's 4.49 seconds. Not sure why it's the same, but we can probably, there's a reason for that. We get the speed from the velocity, the max velocity is 0.611.
Mm-hmm.
Potential energy. So we have to pause it at some point. Now it says on the way down. I don't really know what that means. Like, let me. So when it gets to the end, it's on the way down like that. So like these two numbers have to add up to the 0.374. And you'll see that that's not changing. So we got 0.0187. And then the other number is 0.355.
0.355. Okay.
Okay. So the only thing that we're going to change is the amplitude according to this. So some other, we might go, I don't know if we can just, but let's go like 7.5. Let's go 2.5. Let's go 15. Or maybe 20. And then we're just going to record the information in here. Do you want us to continue with this?
Yes, let's keep going.
Okay. So I'm going to reset. I'm going to change the amplitude to 2.5. And then I'm going to start it again. So the oscillation period is still 4.49 seconds. Really not sure why that isn't changing. The maximum bob is 0.218. Oh, that's 0.218. So we're in this one. What did I say for the string length? Oh, that is the string length. Oh no, that's the same. We didn't change that. The time is still 4.49 seconds. And what we should see is a decrease in the maximum velocity because it's not swinging as fast. So 0.306.
Yeah, it did decrease, right?
Okay. And then the total energy is here. And I'm just going to do it right in the middle, kind of ish, 0.0934.
934.
Okay, so the energy is going down because it's not swinging as fast because energy is conserved in a pendulum, 0.0656. And then 0.0278. Okay. All right. Well, let's go to 7.5. We will reset 7.5, and we will we'll start this thing here. And that period is still the same. That period has to do with it's like 2 pi square root of 2 pi over L or something, since we're not changing that anymore. It's probably why the period's the same. The elongation is 0.654. And the time is still 4.49. So the speed should go up. It should be between these two numbers. Velocity, yeah, 0.0917. Okay, energy. Energy we got to grab from the energy graph here. Pause it somewhere in the middle. 0.840 joules.
Mm-hmm.
All right, and then we'll grab the potential, the kinetic 0.218. And then the other one is 0.622. All right. So we should see some big jumps now because we are increasing the amplitude now quite a bit. Should so reset, doubling it now. So we're going to see some big differences, I think, this time. Maybe not. Not as much as I thought. Well, actually, these axes just rescaled. So the elongation here is 1.31. That must be the bob. The time is still 4.49. Max speed, velocity here is 1.83. And then we'll get the energy here again. So the energy, 3.36 joules. And then the two other numbers always add up to this 1.42, 1.94. And then we got one more to do here. We got reset, amplitude of 20. Okay, let's start this thing with elongation. So 1.75. The time there is still 4.49. Velocity is 2.44. And then the energy is 5.98. See that energy is going up as we increase the amplitude, 2.33. And then it's 3.64. Okay, so that's your data set. That's all done now. It's asking, is mechanical energy conserved as the pendulum swings? Basically, it's like in the graph, actually, this thing illustrates it the best. These two always combine to the same number no matter where it is in its oscillations there. All the potential energy is converted to kinetic energy, and all the kinetic energy is converted to potential energy, and so on. All right, so now it wants you to do an analysis. This is where you draw conclusions.
Based off of your data.
Yes, you draw conclusions. Boy, this is formatted weird. Draw conclusions from the data. So I'll just put some bullet points in here, and I would suggest that you convert them to here. So holding mass constant, ... What did we notice? Well, we also held the
period was constant, right?
pendulum. Yeah, but that's because we held the pendulum length constant also. So we noticed that the period was always the same. Okay. What else do we notice? We noticed that potential energy plus kinetic energy always equals total energy, no matter what.
The amplitude seemed pretty sporadic. But
So
wasn't
as the amplitude increases, so we set that. We set the sorry, let me get this in there. We set the amplitude. So you need to say things like as amplitude increases. Well, what else did we notice? We noticed
max speed
that
increases, right?
max speed increased.
Does that also increase the is it
Total energy increased.
what about potential energy? Does it increase potential energy and kinetic energy or not?
Potential energy and kinetic energy are part of total energy, so you can break those up and say they both increased because they did, or you can just say total energy. The bob height also increased. So you can leave this up to yourself. You don't want to. You can decide whether to talk about potential energy, kinetic energy, or simply energy in general. All right. Okay, so errors, and these don't have to be long. I don't know what they're telling you in class, but they don't have to be long. So there's two types of errors. The first is random errors, and these occur from these are natural variations around the measured values. Okay, so this is not a good example of this, but it's like if I told you to go measure the width of the road, like, and let's say the true width is 30 feet wide, and you came back and you said, oh, it's 30.5 or 29.7.
29.5.
Yeah,
Yeah.
those are random errors. Those are natural variations around the accepted values, maybe true values. Okay. The second type are systematic errors, and these are based on uncalibrated equipment or simply measuring the wrong thing, for lack of a better word, over and over again.
Okay.
And so, for example, just using our road analogy, let's say I handed you a measuring device that measured it in it measured something else completely, but you kept coming back and telling me it was 400, or you're like, no, now it's 401, now it's 402, now it's 399. These values are still they're still sort of centered around a value, but they're completely wrong. They're completely bogus. Okay, so you actually don't have either of these in this lab. So what I would suggest doing is I would recommend um, describing the errors, describing the possible errors, which is below, then stating there are no errors because the software used is, for lack of a better word, is perfect. So
Imperfect. Yeah.
software doesn't make mistakes. Okay. There's also other things you're supposed to do in here. I don't know why there is so much space. That is me. Let me see if I can clear this up. This is unbelievable. Remove space before paragraph. Okay. The other part of this that you really need to say is that the experimental data proves what is known theoretically.
All right.
And that statement there says to, like, that's what you're trying to do. They're trying, like the reason you're doing this lab is because something is already known to be true, and they're just trying to get you to see it experimentally. You are not uncovering anything new here, and that's why this is always a good statement to say here. The experimental data proves what is known theoretically, and this is where you actually have to say that energy is conserved in a pendulum. So like this state here, you ever write, whether it's physics, chemistry, digital logic, whatever you got, if you go into engineering, or whatever science you go into, but you really want to say it for what specifically it is.
All right. Okay. So I'm gonna put this all together.
I've written, make sure you rewrite this in your own words, because the instructor will know that this is not your words.
Mm-hmm. That is
That's just
true.
a recommendation. You do whatever you want.
Yeah, I'm not gonna be like copy pasting. That's kind of sad to do.
Yeah. Well, people do that, and it gets into all kinds of trouble.
Oh yeah,
I'm happy
plagiarism.
to help. I'm happy to tell you the things that are needed, but always do this in your
Ultimately
own.
up to me. Yeah, there's
Yeah.
you can't you can guide a horse to water, but you can't make it drink it.
Right.
All right. So I put in the data table into another one. All right. Analysis. Please scroll down to the analysis real quick for me, please.
You want me to scroll down?
Yes, please. I'm
Okay.
gonna draw this down on a different document. All right. So while holding mass. Excuse me. The same.
Appreciate it. That's sad, man.
So while I'm gonna try that. While holding the mass and pendulum constant, the period always remained the same, and the potential energy and wait, that's a run-on. All right, period. Let's see. What? So I should put potential energy plus kinetic energy equals total energy no matter what. Okay. You said the amplitude. This amplitude increases. Okay. Was experiment. All right, here's what I have for my analysis. But while holding the mass and pendulum length constant, the period always remained the same. Potential energy added to kinetic energy equals total energy no matter what throughout the experiment. After setting the amplitude, the max speed increased, the total energy increased, and the bob height increased as well. Should I add something else to that?
It sounds good, but it is if we're being really critical, it doesn't have any
Substance is kind of bullet pointy.
it is. I mean, you just converted what I wrote here to bullet points, which is fine, totally fine. It's just that you want to at least give you like a topic, like really should have a topic sentence, like meaning like what's kind of the summary of this lab, which is that the conservation of energy holds true. So the something that says the analysis of the data, experimental data, demonstrates that the conservation of energy holds. Either, and I like it there. You could also put something at the end, but I would include something like that. And you're welcome to use those words, but
All right. All right, on to experimental errors. Could you scroll down to that
Yep.
for me, please? Excuse me. All right. Let's see. All right, here's what I have. There were random errors such as natural variations with different values, as well as systematic errors. Wait, this is too monotony. Let's see. I'm gonna put examples of natural experimental errors include natural variations with different values, as well as systematic errors, which can this can simply mean measuring the wrong value over and over again. This feels a little bit. Examples of natural experimental errors include natural variations with different values, as well as systematic errors, period. This can simply mean measuring the wrong value over and over again. That's the problem. I put this two times. The data in this experiment is that energy is conserved in a pendulum. Is that okay?
As long as you get each of these points down, your instructor will be very impressed with you. So they should be. It's always good to write something, then come back and look at it, in an hour or in the morning or at a later time. That's how the best writing is done. It's never done in the moment.
That's true. All right, I gotta put hypothesis in there.
So your hypothesis is whether or not you think conservation of energy occurs as a pendulum swings. It's pretty easy to write it as a result of what we did, but most of the time you're trying to prove the thing that they're asking you about.
I'm just gonna put if a pendulum swings, then mechanical energy is going to be conserved.
Yes.
All right. Can we put something? Do you want to put something for the problem and the question right here? Is mechanical energy conserved as pendulum swings, or do you think it's not?
I think this is like the question being posed to you as like sort of the topic of the lab.
Okay, so I don't think there needs to be a answer to that.
No.
Okay. I think that's everything I wanted to get through with the lab. Now
Great.
I'm gonna send you some pictures of not a picture. That's stupid. I'm gonna send you a worksheet real quick. I'm gonna open up in a doc. Thank you very much for helping me with that lab. I really appreciate the help.
That went well.
I think that's pretty smooth. I appreciate your help. Let's see if I can. I don't like this. I don't like the way this is made. Excuse me. What can we do? What can we do? It's one of those situations where the instructor gives me a document, but when you open it up in an actual like Google Docs, it like overwrites like all of the stuff that you're supposed to show.
You can email it as a Word document. I'll open up in Word.
Oh yeah, I can
do whatever you need. You can also convert them to PDFs. You can just save it from your Word document as a PDF. Lots of options.
Good idea. I'm gonna send it to you right in the reply. Attaching it. There we go. Give it about a few seconds and it should pop up. Excuse me.
Not seeing it quite yet. I'm sure it'll be here shortly. All right, there it is. Simple harmonic oscillators worksheet. Okay. All right, I'm going to snip in. I'm going to snip in the question. Then I'll share my screen and we'll get started here. All right, so if you're seeing my screen, you see see this. So it says here 10 complete oscillations. That's 10T, I believe the instructor's meaning 10 periods. It takes 45.6 seconds. So we can figure out the frequency if we want. First thing he asks here is how long is the cable that the professor is writing? Okay. So we have for part A, we have that the period is 2 pi square root L over G. Is that okay?
Sure is.
Okay, so that's the governing equation. So we have to solve this for L. L equals T over 2 pi. You square that, and then you multiply by G. So it looks like G T squared over 4 pi squared. So 10 periods takes 45.6 seconds. So if we divide both sides by 10, 1 period is 4.56 seconds. Is that okay? Because we're going to use that value in this analysis here, 4.56 squared over 4 pi squared.
I'm going to be printing out the problems real quick because it's pretty difficult to do this just by computer. All right, I got the first problem out. There we go. Do you want to put the knowns and the unknowns in the formula down in the little space that it provides, or no?
I can. I can definitely do that if you'd like. So, kind of already done some of those. So I'll just move those things over. The knowns. The knowns here is that 10 periods takes 45.6 seconds. That is all that is given. The unknowns are the length of the pendulum, and the formula here is, and I don't know which one it wants you to start with, so I'll just start with the kind of the one that's usually shown
guiding one, yeah.
Equation sheets. So that's for part A.
All right. Did we find part B yet?
No.
Okay.
No.
All right, let's move on.
All right, so part B, the knowns here is the period. We know that 1 period is 4.56 seconds.
Mm-hmm.
The unknown is F, and the formula is F equals 1 over T. So that's 1 over 4.56.
Fair enough. All right.
For part A, we never got a number. That's this up here. If you need me to, I can put that into a calculator. Get out the result here, 9.81 times 4.56 squared divided by 4 and pi squared. Should always check these. Sometimes I put them into the calculator wrong. This one's 5.17 meters. Okay, can we move on to number 2?
Yes.
All right, number 2. So for number 2, I got to stitch this in a special way. That way I get the things you want. All right, so here's the question. And then let's do a knowns, et cetera. Okay. All right, knowns. A powerful experimental sewing machine is powered by a mass spring system. That's interesting. How many stitches can this machine stitch in 1 second? This is a measure of the sewing machine's free period or frequency. Okay. The known here is that there are 1,500 stitches per minute. The unknown is the period. Now period, I don't know why T is used, but there's probably a reason for that. The period is always like, I'm going to call it instances per unit time.
Okay.
And it's generally 1 over s. So time is in seconds. So in your case, it's 1,500 stitches, but that's in 1 minute. So we need to convert that to, well, in 1 minute there are 60 seconds.
True.
So 1,500 divided by 60 is 25 stitches per second. And that's your period.
For 1 minute times 1 over 60s equals 25 s stitch per sec. All right.
So frequency, sometimes this is preferred. It's how much can you get done in 1 second, and that's why it's 1 over the period. It's 1 over 25. It's, you get 0.04 done. That's what 1 over 25 is in 1 second.
For A1, for AI, I mean for I, is it period? Is that what we were looking for?
Yes, we found the period. We actually found both, but this is the period, and this is the frequency down here.
All right. Period T equals, excuse me, F equals 1 over T equals 1 over 25 equals 0.04 S.
All right, part B. So in part B, we're trying to find the how large is the mass. So we're trying to find M. I kind of like to go back to the formulas because I don't know I don't remember them very well. 2 pi square root m over k.
Sure.
So the given here is k is 0.5 newtons per meter. That's a spring constant. We also know the period. The period is what we found in the previous one. It's 25. We don't know m, so we need to solve this for m. So that's t over 2 pi equals square root m over k. Square both sides, so t squared equals 4 pi squared equals m over k. So m equals k t squared over 4 pi squared. Your k is 0.5. Your period is 25 squared over 4 pi squared.
I'm going to go get my calculator.
Okay. Let me throw these numbers in myself. I get the mass here of mass is equal to 7.92 kilograms.
7.92. All right. On number 3.
Question 3 here. An astronaut travels to faraway moon with a 1.5 meter long pendulum. That's your L there. She finds it takes 6.0837 seconds to complete one full oscillation. So that's the period. The period is 6.0837 seconds. What is the acceleration due to gravity on this moon? Okay, so we know L and we know T, but we don't know G. Okay, we don't know G, but we do know a formula. If I can get back to it, we know from one of the formulas that's 2 pi square root L over G. So we're now going to solve for G. So it's T squared over 4 pi squared equals L over G. That's just a simplification here. You cross multiply to get G out of the bottom. 4 pi squared L. So G is equal to 4 pi squared L over T squared. We have all these quantities, 4 pi squared. We know that L is 1.5, that's given. We know that the period of oscillations is whatever, it's 6.0837. Okay, and just punch that into the calculator and get a number here. 4 times pi squared times 1.5 divided by 6.0837 squared. It's about 1.6. You're supposed to do like a units analysis, but it's meters per second squared is G. It's the same as acceleration.
Mhm.
So that's part I. Okay. And then part double I, if this pendulum were brought back to Earth, how would its frequency on Earth compare to its frequency while on the moon? Ooh, this is one of those conceptual questions. So we know that the, let's grab a formula here. We know that T, this is part double I, T is equal to 2 pi square root L over G. And we know that period is equal to 1 over F.
Mhm.
So frequency is equal to 1 over the period. So the frequency is equal to 1 over 2 pi square root G over L. That's that. I skipped all the simplifications of that, but that is what we see there. So what is the same? So we've got Earth, and then we've got this moon over here. So what's the same and what's different about them? Is the length of the pendulum, does that change? No, you're bringing it back, so that's the same. But this G is different. What is G on Earth?
G on Earth is 9.8, right?
Yep, G on this planet is 1.6.
Oh, that one
So,
is 1.6. Okay.
so this is the same. This is the same. L is the same. The only thing that's different is this. So what's the difference between the square root of 9.81 versus the square root of 1.6?
A lot. Big difference.
Right. Well, this one's bigger. This one's bigger.
Yeah.
So the frequency is going to be larger here, and the frequency is going to be smaller here.
Okay.
And conceptually, that's what it's asking for. There's not really like a knowns, unknowns, and a formula for this one. Are you trying to get through all of this?
Yes.
Okay, we can pick up here in about 10 minutes. We won't have enough time to finish, or you could keep working on this on your own if you wanted, but we can pick up here in about 10 minutes. We'll obviously have more time if you want to do some other stuff, but I need a short break, and
That's fine. I'm
I'll be
fine with
back
it.
with you shortly.
I'll see you later. Bye-bye.
Thanks, Jack. Bye.